Okay, so welcome to the to week 10 tutorial. So what we have today, we have a portal frame ABC. Okay, so column AB has got a stiff flexion rigidity of 2 EI, and the beam BC has got a flexion rigidity of EI. BC is subjected to a concentrated load of 100 kilonewtons at midspan. Both supports A and C are fixed. Okay, and the question is, or the questions are, determine the moment at ABC using moment distribution method, and then draw the annotated bending moment diagram for the frame showing all the intermediate values of bending and the position, the maximum bending and the position of any points of contraflexion. Okay, so okay, so let's get going. So what's the first thing we need to do here? Step one, as usual, fixed moments. Okay, so so we start with the fixed moments here for this frame. Okay, so just for my own purpose, let me draw it here. Okay, so we have 4 meters for the column and 4 meters as well for the beam. Okay, and it's and then we have a UDL, sorry, not a UDL, a concentrated load of 100 kilonewtons at midspan of the frame of the beam. All right. So first thing, step number 1 is to determine the fixed end moment. Okay. Now we can see that AB is not loaded. So we can see here the column is not loaded. Okay, so AB not loaded. Okay, and therefore what does it mean? No fixed moments. Okay, so FEM AB is 0, and FEM, the fixed moments at B, is also 0. Okay, so the fixed moments at A and B in this case are 0 because the AB is not loaded. Then we have member BC. Okay, member BC, we have a load in the middle, 100 W, 100 kilonewtons. Okay, in the middle, and the span is 4 meters. Okay, and the so we have B, C, and these are the fixed moments, clockwise, anti-clockwise at B and clockwise at C, using the table. So if you look at the table of the fixed moments for this case here, then you can see that the fixed moments are equal to WL over 8. So we have FEM BC, this is the fixed moment at B, is minus WL over 8, which is minus 100 times 8 times 4, sorry, divided by 8, which is minus 50 kilonewtons meters. And the fixed moment at C, that's CB then, is plus, is exactly the same because we have symmetry, so it's a plus 50 kilonewtons meters. Okay, is that okay for the fixed moments? Yeah. Now next step is, now we are going to determine the distribution factors. Distribution factors at the joints. Okay, so now we are going to determine the distribution factors at each of the joints. We have joint A, joint B, and joint C. At joint A and C, we know that the distribution factors are equal to 0. So we have, for joint A, we have DFAB. There is only one member connected to A and the wall, obviously, so it's going to be 0. For joint C, we have one member, CB, and this is going to be equal to 0 as well. Okay, And for joint B, we have two members. We have DF B AB, BA, okay, and we have two members. We have member BA and member BC connected to joint B, okay. So DF BC, right? So what is it? What's the definition? So what is the distribution factor in this case for BA? For BA,
1/4.
we have, remember we have two EI for BA and EI for for BC, okay? So we have 2/4, isn't it?
Yeah, 2/4.
And then the sum 2/4
Plus 1/4.
plus 1, because we have 1 here, 1/4. That's it. And then you can see this is equal to 0.5, okay? And similarly for BC, this time BC we have 1/4, okay, divided by the sum of the members connected, the stiffness of members connected to joint B, okay, which is 2/4 plus 1/4 equals, again, equals 0.5 as well. Have I got this right or not? 2/3, sorry, what am I saying here? 2/3, I do apologize. 2/3 and 1/3, sorry, not 0.5, 1/3, okay? And you can see that the sum is equal to 1, okay? So we have 2/3 for DFBA, and the distribution factor for BC is 1/3, and the sum is equal to 1. Is that clear? Yeah? So what's next?
The computation thing.
Yeah, so now we are going to build the moment distribution table for the frame. Yeah, so now it's the moment distribution table, right? So let's do, if you have any question, just stop me, okay, please? So now we do the moment distribution table. Are you okay at the back? Yeah? Can we move on? Next one. Okay, thank you. So now we do the moment distribution table. Okay. And so what we have in the first, so this is our table here. In the first row, we put the joints, okay? In the second row, we put the members, then the distribution factors, and then the fixed end moments, okay? Now, in this case, because we've got only one intermediate joint, you can see we've got only one intermediate joint and the two members connected to that joint, so we don't expect many iterations, okay? It will be very quick, all right? So joint, we have joint A, okay? We have joint B and joint C. There is one member connected to joint A, and that is AB. Joint B, we have two members. We have member BA and we have member BC. And finally, joint C, we have only one member, and that's member CB. So, and these are the, okay, these are the joints and the members, okay? Distribution factors, we have the distribution factor at A is 0. At B, what was it? At B, it's 2/3 here. Okay, so we have 2/3. For BC, we have 1/3, and CB, we have 0. Then distribution factors. AB is not loaded, so we have for BA, it's AB is 0, and BA is 0. So we have 0, 0.
So it's members A, B, right?
That's AB, sorry, yes, of course. Okay, and then for BC we have minus 50 and plus 50 for CB, okay? So we have minus 50 and plus 50 and these are the fixed end moments from that we have calculated. Right, now we have an out of balance, because remember here we are balancing moment joint B. This is the intermediate joint, okay, that we are balancing. Okay, so we have a joint B, and you can see that at joint B we have an out of balance of minus 50. Okay, we have minus 50. So what do? We balance. So the first act, the first step is to balance. How do you balance? We balance by multiplying the out of balance moment by the corresponding distribution factors and change the sign, okay, because we are balancing. Okay, because what you want to get rid of the out of balance moment. So we have minus 50 times 2/3, I think it's 33.33 with a plus, and 50 times a third is 1667, okay, with a plus. And you can see if you add these two together, if you add up 33.33 plus 16.67, you get exactly plus 50, which will balance the out of balance. So when you add these two, when you add up these two together, you get exactly plus 50, which balances the minus 50, and that's why we call it balance. Okay, then A is fixed. You see, joint A is fixed, so therefore we are going to carry over from B to A half. So from BA you carry over within the same member. You carry over within the same member. So we're carrying over from B to A. Remember BA, AB. You see BA, AB. So we carry over half. Half of that, which is 1667. This is carry over. Okay. And similarly, because C is fixed here, you can see that joint C is fixed. So again, we carry over half. 1667 divided by 2 is 883 or 33, isn't it?
8.34.
Yeah. Okay. So now there is nothing else to do. So we are going to draw a line here and check the equilibrium. Okay. So we're going to draw a line and check the equilibrium. 0 plus 33.33 is equal to 33.33 with a plus. Minus 50 plus 1667 is minus 33.33. And you can see what we have. We have equilibrium. Okay, we have equilibrium. And that's all we need. That is all that we need, is to have the joint, the intermediate joint, in equilibrium. So the intermediate joint here is now in equilibrium, and therefore we have done, achieved the objective. Now we can determine the remaining final moments. Okay, we determine the remaining final moments. So we have 0 plus 1667 is plus 1667. Okay, plus 50 plus 833 is plus 5833, and these are the final moments for this frame. Okay, very easy, very simple, because we've got one intermediate joint and it is in equilibrium. We have achieved equilibrium, and therefore these are the moments for the frame. Okay, so the next step now is to use the moments from the table to draw the bending moment diagram for this frame. Okay, at the back, yes. Okay, thank you. So let's look at now the so this is what we have. Okay, this is the frame. Okay, we have a point load here. We have a concentrated load there. Okay, now, so we have A, B for the column, and then we have B, C for the beam. Okay, now look at this carefully. We have 16 at joint A, we have 1667 clockwise. So looking this way, so we have clockwise 1667. Okay, then at B we have clockwise again, because it's positive, so it's clockwise 3333. Okay, so that's also clockwise. Then at B, on member BC, at B we have anti-clockwise 3333. Okay, and finally at joint C we have positive clockwise 5833 clockwise. Okay, and these are the moments from the table, okay, with the correct directions. Okay, anything positive is clockwise, anything negative is anti-clockwise. In order to draw the bending moment diagram correctly, now what we're going to use use our convention, and that is that we always plot the diagram on the side of the beam where there is tension. So, for instance, if you look at A here, where is the tension? Left or right?
Right.
Do you agree the tension is on the right here? So we have tension there. Okay. How about at B? Left or right?
Left.
Yeah. So the tension is here. At B, top or bottom?
Top.
Top, yes. At C, again the tension is at the top. So we have got the tension there shown on which side. Okay, you always show where on what side of the member the tension occurs. And now with this here, with this information, we can plot now the bending moment diagram for this frame, which I'm going to do here. Okay, so we have top, at the top there we have 5833 at the top. Okay, and then at the top there we have 33.33. Then on this side of the member, on the right, on the left, sorry, we have 33. Okay, and then on the right side there we have 16.67. all right, and because there is no loading there is no UDN, nothing, so basically all we do is join these points together with a straight line. Okay, we have a point load here in the middle. We have a point load, so therefore the bending moment diagram will be linear, and it's going to be something like this. Okay, all right, and this is the bending moment diagram for this frame. Is that clear? Okay, now the only thing we need to do now is okay, I mean, first of all, if you want to assign, if you want to give signs to the diagram here, the convention is that we use sagging positive, hogging negative. For instance, the 33.33, is that sagging or hogging? 33.33, hogging or sagging?
Hogging.
Yeah, because it's making it bend down. It's bending down like this. So you see at B, it's bending down like this. That is hogging. Yeah, so therefore this is minus. And similarly there at C, you can see it's bending down, so that is hogging as well, right? If you come here, if you come there at B, it's bending this way. Can you see it's bending this way? So that's hogging. At B, it's bending like this. Okay, it's bending this way, right? So therefore this is sag. Okay, according to our convention. And these are the signs that you can attribute to the bending moment diagram using the sagging hogging convention, which you don't mix with the clockwise anti-clockwise, as I have explained a number of times already. Is that okay? Okay, so this is the bending moment diagram with the with all the values shown. The only thing we need to do now is to determine what the intermediate values are. We have 1 point of contraflexion to determine here, okay, and we have another 2 points of contraflexion on BC, and obviously the maximum moment. So we need to determine the positions of the point of contraflexion and the maximum bending moment for this frame, and that will give us a fully annotated bending moment diagram for the frame, right? So I'm going to isolate. So in order to determine the intermediate values, we are going to analyze each segment in isolation. So we are going to analyze AB, then we analyze BC. Is that clear? Okay, so let's start. Any questions? Anything at all? So let's start with member AB. Okay, that's the column. So let's do AB here. So AB. So this is now intermediate values. Okay, intermediate values. Okay, and we have. So let's start with AB. All right. I'm going to turn it around for ease. Okay, so I'm going to turn around the column just for ease, actually. All right. So what I have AB. So at B we have a. You can see here we have a clockwise moment 33.33, and we have a clockwise moment again. You can see at A of 16.67. Okay. So in addition to the moments, obviously we have reactions. So we have a reaction at A VAB. Okay, they are not really vertical reactions. They are really horizontal. Okay, but it's just for ease and convenience. So we have VBA. Okay, and the distance is 4 meters. Okay, so let's determine the reaction forces. So we have taking moments about B first of all. So we have clockwise VAB times 4. Then we also have clockwise 16.67, and we also have clockwise about B 33.33. So everything is clockwise in this case. VAB times 4, 16.67 is clockwise, and 33 is also clockwise about B, and there is nothing else anti-clockwise, so that is about B, and that is equal to 0. Okay, and this gives, please do check it. Okay, please do check it. It gives, I think, a moment. Can you check the reaction? Sorry, AB.
12.5.
Sorry.
12.5.
With the minus.
Yeah.
Okay, thank you. So we have a. So the reaction at A is 12.5. And now let's work out the reaction at A. So we take now moments about A. Clockwise moments about A, we have 16 and the 33. So we have 16.67 plus 33.33. These are clockwise about A. And then we have anti-clockwise about A, VBA. So equals VBA times distance 4. And that gives a VBA of, what is it? I hope it's 12.5 plus. It should be.
Yeah,
it is 12.5 kilonewtons. Okay. Now you can see that the equilibrium is checked. So we have VAB plus VBA is minus 12.5 plus 12.5 is equal to 0. And you can see there is no vertical loading on the member here. There is no loading. The member is not loaded. So therefore the equilibrium is satisfied because there is no loading. All right. I can determine now this point of contraflexion here. How do I determine the point of contraflexion? Yeah, take a cut. So I'm going to take a cut. So I'm going to take a cut there. All right, at a distance x, and I have M at the cut, M is VAB times the distance x plus 1667, which gives, we substitute AB, so AB is minus, so minus 12.5 x plus 1667, and this is the expression of the bending moment at a cut at a distance x from A. Right? So what do we do now for the point of contraflexion? We put M equal to 0. Okay? So point of contraflexion, M is equal to 0. So therefore, minus 12.5 x plus 1667 equal to 0, which means that if we take this to the other side, so we have 1667 is equal to 12.5 x, and that gives x. Can you please check x for me, please, which is 1667 over 12.5?
1.33.
1.33 meters, and that's from A, okay? From A. So it's 1.33 from A. So the point of contraflexion here is actually at 1.33 from A. Okay? Is that clear, everyone? Right? So this is the, so we've got the first, so we've got this here. So this is 1.33 meters. Okay? That's the point of contraflexion position from A, 1.33. Any questions? Okay, so now what next? Next is to analyze now BC. Yeah, so now we're going to analyze BC and then determine the position of the points of contraflexion as well as the maximum moment. Is that okay? So member BC now. So member BC. So this is member BC. This is what we have. We have BC, okay, with an anti-clockwise moment at B of 33 and a clockwise moment at C of 58.33. And then obviously we have the reactions. We have VBC and VCB, and the span is 4 meters. Okay, and remember there is a concentrated load in the middle, okay, of 100 kilonewtons. Okay, so we have a concentrated load of 100 kilonewtons to include, to take into account. So first of all, let's work out the reactions. So let's work out the reactions. So reactions. So we take moments about, let's start by taking moments about C. Anything clockwise for equilibrium, clockwise moments equals anti-clockwise. So about C, what clockwise moments have we got about C? We have VBC, the reaction, times 4, that's clockwise. Okay, we're taking moments about C, plus, and then clockwise we have 58.33, isn't it? That's it. And then about C, anti-clockwise we have 33.33 and 100, so plus 100 times the distance, which is 2 meters. And that's it, okay? And please check it. So we have 4BC. So 4BC will be equal to 33 plus 200, and then we take this to the other side, so minus 58.33. So you add up all this together, divide by 4, and that will give you VBC. Can you check? I've got 43.75, but please do check it.
Yeah.
Is that correct?
Yes.
43.75 kilonewtons. Okay, and this is the reaction at B. Now we take moments about B. So now we're taking moments about B here. So clockwise moments about B, we have 100 times 2, that's clockwise, and then we have the 58, so 58 33, that's also clockwise, and then anti-clockwise we have the 33.33, and we have also VCB about B, VCB times 4. Okay, and that gives 4 VCB. So I'm going to take the 33 the other side, so 4 VCB is equal to 200 plus 58 33 minus 33.33, which gives, please do check it, VCB
56.25.
yes, I've got 56.25 kilonewtons. Okay, now is this correct?
Yes.
Yeah, so check. So we check VBC plus VCB. The sum of these two is 100, isn't it? And this is equal to the applied load of 100. So therefore, it's okay. Okay, so therefore, it's okay. And this is the check for vertical equilibrium that you need to make in order to ensure that your reactions are correct, because we all make mistakes. So if you make a mistake here, the vertical check equilibrium, the vertical equilibrium check will tell you whether your reactions are correct or not. Okay, so we've got the reactions. So VBC is 43.75 and VCB is 56.25. So what do we do with this? We take a cut. So now we're going to take a cut there. I'm going to take the origin at B, and we are going to take a cut at a distance x from B. And we are going to take a cut at a distance x from B. So what is the bending moment at the cut? Can you tell me what is the bending moment there at this cut here?
Negative 33.33.
Yeah, so it's the reaction times x. So it's 43.75 times x. Anything else?
Minus 33.
Yeah, because this is hogging. Yeah, this moment is hogging. So minus, okay, 33, and that's it. Okay, VBC is sagging, so it's a plus 43.75 times the distance x, and then minus, because it's hogging, 33.33. Remember, this is a moment, so you don't multiply a moment by the distance again, because it's already a moment. Okay.
Why didn't we take it after the 100 kilonewtons?
Yeah, we have to do both. Okay, so that's the first cut. Okay, and let me call this number 1 here. Okay, so this is cut 1. Okay, because why we need to do it twice?
Now I have 2 points.
Because we have 2 points. So I'm going to take a cut between these 2 points, and then I take another cut. Or you could use Macaulay's, so you take only one cut there, but you need to be careful with the square brackets. All right, is that clear? All right, I mean, in this case it's simple because we only have one load, so we can take 2 cuts. Okay, so what's the so this is M. Okay, so in order to find the point of contraflexion, what do we do?
Set M equal to 0.
Yeah, so basically points of contraflexion. Okay, so the point of contraflexion, we put M equals 0, isn't it? And that gives 43.75x equal to 33.33. If you can give me the answer, please. I've got 0.76.
Yeah.
It is correct? So 0.76 meters from A. So this is the first point of, from B. Okay, this is the first point of contraflexion. what is the bending moment? You know, what is this moment here? What is the bending moment there? How do we find the bending moment there?
X equals 2.
Yeah, so we put x equals to 2 here, isn't it? Yeah, so if you want the bending moment where the load is, you put, okay, at x, or for x equals to 2, which is where the load is applied, where the 100 kilonewtons is applied, okay? The moment is, which is the moment at mid-span, isn't it? So that's the moment at mid-span, okay? So the moment at mid-span, which is for x equals 2, is 43.75 times 2 minus 33.33, right? And that gives, so m mid-span will be, can you check the answer, please? I got 54.17, but I need you to check it, please. 54.17 kilonewton meters. That's the moment at mid-span. Okay, so which is what we have here. So we have 0.76 for the point of contraflexion, 0.76, and the moment here is 54.17. So we have 54.17. So we have 54.17 there. All right. So we have the moment is 54.17. Okay, and the point of contraflexion is 0.76. Now we are going to take another cut there to determine the second point of contraflexion. So I'm going to take another cut here, okay, from the same origin. So this is cut number 2. So we take another cut between the mid-span and the and point C, and this is cut number 2. So cut number 2. Can you tell me what is the bending moment at cut number 2?
Minus 100.
Here. Sorry? So we have 40, it starts with the reaction. We have 43.75 times the distance to the cut, x. Yes? And then this so minus 33.33, and then now you need to add the load here, isn't it? So minus 100 times that distance, okay, this distance, which is x minus 2, okay, x minus 2, and this is the moment at that point, okay? All right, okay. This is, if you want, I put it between bracket here. It's for x between 2 meters and 4 meters. Okay. So let's develop the bracket here. Let's expand. So we have 43.75x minus 33.33 minus 100x minus by minus plus. So we have plus 200. What does it give, please? Minus, yeah, so you take the this to 43.75 minus 100 is 56.25x, yes, and then we have minus 33.33 plus 200, which I believe is 1667.
Yeah, 167.67.
Yeah, and that's the expression of the bending moment at cut number 2. So for the point of contraflexion, we put m equal to 0, and therefore we have, when you put m equals 0, that means 56.25x, okay, plus minus plus 166.7 equal to 0. That means x is 166.7 67 divided by 5625, which gives, is it 296?
Yeah.
296 meters. Again from A. Remember, we kept the same origins, so that's from A. As a check, if you put, listen to this here, if you put x equals to 2, you should find the same answer as this one here, right? Because the bending moment is the same left or right, okay? So if you put x equal to 2 here, you should find 54. Do you want to check it? So put x equals to 2 here, you should find the same value.
Yes.
Yeah, exactly. Okay, thank you. So so we have the point of contrareflection is 2.96 from A. So this is the distance. So we have 2.96 meters. Okay, we have 2.96, and this is a fully the fully annotated bending moment diagram for this frame. Okay, with all the intermediate values of points of contrareflection and maximum moment indicated. Okay, it's very simple. As you can see here, it's exactly the same steps, the same analysis are for continuous beams. There is absolutely no difference whatsoever. It's exactly the same, right? Uses the same rules, same equations, same steps, everything is similar, whether you've got a frame or a beam, and whatever the complexity of the frame, it's exactly the same steps we follow all the time. All right? Okay, and we finish this example. Have you got any questions at all? Anything? Okay. I mean, in the live session, we are going to do another frame, so that gives you enough examples to work on when you are revising. Okay. Right. So if you haven't got any questions, I'm going to stop the recording. Thank you.